So in this video we're going to develop the solution technique for first order linear differential equations. So a first order linear differential equation is going to have the form a of x times y prime plus b of x times y equals c of x. And there's a very specific solution technique for this type of differential equation. So we're going to walk through what the idea is for the solution process. So we start off with a of x times y prime plus b of x times y equals c of x. And the first step is always to get a leading coefficient of 1 on the y prime term. So you step through and you divide everything by a of x. And when we have a of x divided by a of x, as long as a of x isn't equal to 0, that's going to equal 1, so we get the leading coefficient of 1. And then to clean things up, we give these two terms names. So we're going to call this term p of x. So we're going to let p of x equal b of x over a of x. And then we'll give this term a name. We'll just call him q of x equals c of x over a of x. And if we do that, then we can clean up the function so that it looks like y prime equals p of xy times q of x. So we still have a first order linear differential equation. The only difference between the standard form here is that now we have a leading coefficient of 1. And then the idea is we're going to let u, we're going to make a substitution. We're going to let u equal e to the antiderivative of p of x with respect to x. So e to the antiderivative of p of x dx. And we'll see why this is going to be useful here in a minute. So first thing to consider is what is the derivative of u. So if we were to take u prime, what would that look like? Well, if we have e to the crap, which is what we have here, the derivative form is always e to the crap times, by the chain rule, crap prime. So we're going to get e to the crap times crap prime. But what's the derivative of the antiderivative of p of x dx? Well, if we take the antiderivative of p of x and then take the derivative of that result, we'll just get p of x back. The derivative, in a sense, is going to cancel the antiderivation to give us back the original function. So what we wind up with when we do u prime is we get e to the crap. So e to the antiderivative of p of x dx. But the derivative of the antiderivative is just going to be p of x. So this is important. And then what we want to do is look at the product. We're going to take the product of u times y and then ask the question, what would the derivative of that product look like? Well, the chain rule would say you need to take, so not the chain rule, the product rule would say take the derivative of one of the two functions, let's say y, and then multiply it by the other function, which is u, and then we get a plus e, and then we have to take the function for which we took the derivative first, which was y. I took y prime first. Now we're just going to get y times the derivative of the other function, which is u. So we're going to wind up with u prime times y. And the order of multiplication here doesn't matter. So I could just as easily write this u times y prime plus u prime times y. So this is just to take the derivative of u times y, we just take the product rule. And the reason this is useful is we can look at this. Well, what does this look like? Well, this would just be u times y prime, right? But what does u prime look like? Well, we just calculated it. This would be plus e to the antiderivative of p of x dx. U prime was e to the antiderivative of p of x dx times p of x, and this is going to be times y. So what we want to notice is if we go through, on the other thing to note here is that right here the e to the antiderivative of p of x dx is just u, right? U equals e to the antiderivative of p of x dx. So we could actually rewrite u prime as u times p of x, which right here would allow us to do u times p of x. So uy prime plus u times p of x y is the derivative of u times y. And so when I look at my first order linear differential equation right here, what I want to notice is that if I multiply both sides by u, I'm going to get u times y prime plus u times p of x times y equals u times q of x. And this right here is exactly what I have right here, which means that this is just the derivative of u times y. And then you could check your work on this. You could say, what's the derivative of this? It's going to be u times y prime, which I have here, plus u prime times y, but u prime is just u times p of x, and there's the u times p of x. So we can even work backwards to check our work. And then once we get here, what we can do is say, hey, I have a derivative. So if I want to undo the derivative, I would take the antiderivative. I took the derivative with respect to x. If I take the antiderivative with respect to x, I can get back what I started with. So if I do something to one side, I do it to the other. And I know I'm going to wind up with a constant of integration showing up in this process. So antiderivative cancels derivative. We get u times y equals the antiderivative of u times q of x. And I should have put a d of x right there, or sorry, dx. And there's going to be plus some constant of integration. And then I could multiply both sides by 1 over u to get the y by itself. So now I've solved for y. So, and that's the idea behind the differential equation, is to figure out what the y is. So the only other comment here is, yeah, we've solved for y. The question is, can I do this integral? And you may or may not. This integral right here may or may not have a closed form solution. But regardless, you're in a better shape than you were here, and if you have to apply an approximation process, so what? It'll still work out. So the next slide just summarizes this conversation. Hey, if we have a first order linear differential equation of this form, where we've divided that a of x on both sides to get the leading coefficient of 1, it's going to have a solution that looks like this. Y equals 1 over u times the antiderivative of u times the q of x dx. And we actually give this a name. We call it the integrating factor. So you could use, to solve this differential equation, you could use this formula. In the homework, you can't use the formula. So what I want to see in the homework is working through the process from scratch and coming up with the solution. I want to see some muscle memory for the solution process, so that the process and the concept of why it works gets itself embedded into our long-term memory. And working with things conceptually is always better than using a formula. The formula is nice, but don't use it in the homework. And then in the next 1 or 2 videos, maybe 3 videos, I'll show an example of walking through the process on an actual differential equation.